In this video, well, we're going to do a few different examples, but we're going to follow along here to find out what is little g on Earth. And again, if you've been in physics for a while, you of course know little g, oh darn, little g is, there we go, this gets me every time. Little g is of course this thing, right? G is 9.8 meters per second squared. Here's where it comes from. So what we just saw is that little g is this, gm over d squared, where m is the mass of whatever planet you're on, and d is the radius of whatever planet you're on. So when we use this thing here, we're given the values in this question, and in general that's going to be true. Big G, always this. Mass, in this case the mass of Earth, so that's why it's ME, mass of Earth. If you were on the moon or something, you would use the moon's mass and the moon's radius, and you could find out little g for the moon, or whatever planet you wanted to be on, planet or moon or asteroid or anything like that. In fact, I suppose you could even use your own data, your own mass and radius if you were curled in a ball, and you could figure out your own little g. It's going to be pretty small. I've mentioned this before, but do make sure that you're using your exponential button on your calculator. It's for big numbers and small numbers like this. It will help you get the right values. Divided by 6.38, exponential 6. Don't forget to square the thing on the bottom. When I did it, I actually got this number, 9.799088. Little g, approximately 9.8 meters per second squared. Sometimes people use 9.81, depending. It depends a little bit on which of these values you use, right? This value is not an exact value. Probably the mass of the Earth as well. But anyways, this is where this magic number comes from, this acceleration due to gravity. That's where this thing comes from. There's equivalent units as well. I should mention this. Sometimes you'll see little g given in newtons per kilogram. They are equivalent units. Okay, so if I was to kind of talk through this just quickly, we know that force is equal to mass times acceleration. Or maybe you've done this already, maybe you haven't, but force is equal to mass times acceleration. Mass is measured, if you just think units, mass is measured in kilograms, acceleration is measured in meters per second squared, and force then, we give that the unit of newtons. So let's put, we'll kind of put everything in brackets here to show these are just units. This is what people call a unit analysis. Okay, so here's the units for these things. What that means is if you see a newton like this right here, it's the same as kilogram meters per second squared. Okay, so newtons per kilogram, when you see newtons per kilogram, that's equivalent to kilogram meters per second squared divided by kilograms. The kilograms cancel, and you could say that's just equal to meters per second squared. Okay, so these units, newtons per kilogram, exact same as meters per second squared. They're interchangeable. You'll sometimes see g in either unit. All right, so let's try another question. The radius of the moon is given. If the moon's gravitational field strength is this thing, what is the moon's mass? All right, so I'm going to take a quick second, just write some stuff here. Let's write down our given information. Let's say d, in this case, again, it's the radius of whatever planet or moon or whatever object you're on. Sometimes, though, this one throws people off. So hopefully with the discussion we just had, it is not throwing you off. But this is little g. And you could say newtons per kilogram, or you can say meters per second squared. It's the same thing. So the radius of the moon is given. Moon's gravitational field strength. What is the mass of the moon? That's the question mark. Okay, we know little g is given by this equation. Little g is 1.62. Okay, so again, sometimes people get confused. Is this thing here, this thing in the box, is it big G, little g? It's little g, because big G is always this value. Okay, this is never going to change. It's gravitational constant for the universe, for everywhere. We're looking for mass. Okay, mass of the moon, that's what we're trying to find. D on the bottom, this is 1.74, 10 to the 6. And again, don't forget to square that. Okay, I find it's pretty easy for people to forget to square that. To do this math, I'm multiplying both sides by the denominator. Okay, so I'm going to get 1.62 times 1.74 times 10 to the 6. Again, don't forget the squared. And at the same time, I'm going to divide both sides by that numerator. Okay, so we're going to get this thing. We'll work that thing out on our calculator. And I did this one earlier to save a little bit of time. But try it. Make sure that you can do this on your calculator. And again, I always recommend use that exponential button. There's our answer. 3 sig digs. Yeah, true. I should have done 3 sig digs. You can correct it. If we rewrite our force of gravity equation, okay, so what we are kind of figuring out here is this circled thing. Actually, I might have done it on here. I didn't do it. This circled thing right here is little g. Okay, so our force of gravity equation is the remaining mass, this mass right here. Okay, that's kind of coming down over here. Little g is the circled thing. It comes down over here. And we end up with this equation. Fg is mg. This is kind of the, I'll say the shortcut in air quotes. The shortcut equation. So the equation that always works is this guy here. But if you're on the surface of the Earth, if you know what little g is, then you can go ahead and use this thing. So if you want to find your own weight, you can take your mass, multiply by 9.8 because we're on the surface of the Earth, and you can find your own weight without having to use this giant equation up here. A couple things to point out. If you're using our orange textbook at Rick Hansen, there's page 73 is a table of little g values on Earth, just different locations. They're all very similar. They're all basically 9.8. I think in Toronto they say 9.805 or something like that. So you might see slightly different values over the surface of the Earth. They're not very different though. We'll just use 9.8 always. But on page 75 it gives you a table of g values in other locations in our solar system. So we just saw the moon was 1.62. Mars, I think, is 3.62 maybe. They give Jupiter and, you know, all these different kind of planets and some of the moons maybe. So in some of the questions that we do, you may be asked for those. Just check out page 75 if you're trying to find a G value. Or go online, of course. Bob Beeman video, just an interesting one. It kind of has to do with gravity. If we're in class, we may talk about this. I won't ask you any questions on the test, though. All right, on Mars, we know a little g value, 3.61. I was so close. How much would Mr. Gaglardi's space Porsche weigh on Earth or on Mars? Let's go ahead and do Earth first, because this is the easy one, right? Fg is equal to mg, and we know what little g is on Earth. Okay, so the weight, remember when we're talking about weight, that is Fg. Okay, force of gravity is weight. Fg then is the mass of this thing, so 3 times 10 to the 3 kilograms times g on Earth, 9.8. We'll go ahead and multiply those things, and Fg is 29,400, and that is 3 sig digs already. You could say 2.94 times 10 to the 3. That's correct as well. On Mars, if you know little g, which we do in this question, then we can use the same equation. We can just use our Fg equals mg equation again. If we didn't, you could also go and use Fg equals g m1 m2 over d squared. We know the mass of the space Porsche. You would also have to know what's the mass of Mars and what's the radius of Mars. That is in our textbook. You can look it up, or of course you can look it up online. But in this case, we don't need to do those things. We already know this mass, and we're given this little g value. And again, we multiply those numbers together. We're going to get 10,830 newtons. A few too many sig digs there. Let's go ahead and use scientific notation on this guy. 1, 2, 3, 4. Whoops, that's a 4 there. Forget that little tick. That's a nothing. Let's get rid of that so I don't confuse anybody. This is newtons. And I've mentioned this before, but force of gravity, force really is a vector always. You could say down for any of these, but typically when we're doing force of gravity, we are just doing magnitude because we know it's down. We got one last example here. On the moon, a 10 kilogram object. Remember, as soon as you see kilograms, you know this is mass. Okay, so we've got this 10 kilogram object. We know that it weighs 16.2 newtons. Weight is force of gravity. Okay, so I've said that a couple times, but don't forget that. Sometimes people get confused. Sometimes they think weight is mass. It is not mass. Remember, kilograms is mass. Newtons is weight. Oh, dang. Newtons is weight. What's the gravitational field strength? We're looking for little g. So what's the gravitational field strength of the moon? Okay, so this is for part A. A couple different ways we could do this question, but if I'm given the choice, I like the easiest way. The easiest equation is this guy. So if I'm asked something to do with weight, Fg, something like that, I like this guy if I can have the choice. What's the gravitational field strength? Oh yeah, the object here. I lost my train of thought when I was talking. The mass, remember this is the mass of the object. Okay, not the planet. Okay, so the mass of the object is 10 kilograms. What is little g? We go ahead and divide both sides by 10, 1.62. 3 sig digs, yeah, we'll leave it. This is newtons per kilogram, or again, meters per second squared. Same units. What is the moon's radius? And again, probably a couple different ways we could do this one, but I'm going to use this guy. And remember, when we said over here, this was the mass of the object. This one here is the mass of like the planet or asteroid, or in this case, the moon. It's the mass of the, I don't know, the body that you're standing on, if you know what I mean, the astronomical body that we're standing on. We're looking for the moon's mass. So we just went through and figured out this. Little g, 1.62. Big G, always this big thing. Mass, we don't know what that is. But we're given here the radius of the moon. We know that, and I always say it, but don't forget the square. We go ahead and rearrange that, and if we rearrange it, we're going to get 7.35 times 10 to the 22. And try for real. I'm not just looking at the answer up here. Try for real. I worked this thing out. We're going to get that. We could say approximately. That's rounded. But we'll get this thing to 3 sig digs.